This is an ad by Regain Couples Therapy. Let's be honest. Loving your partner doesn't mean you always like them, and guess what? That's normal. Regain, powered by BetterHelp, offers couples therapy that's flexible, affordable, and 100% online. Whether you're reconnecting or working through conflict, Regain is here to support you both. See why people wish they'd tried couples therapy sooner. Visit regain.com/couplespod to get 10% off your first month. That's regain.com/couplespod.
Support American-made tariff-free clothing with American Giant with American Giant. They aren't affected by tariffs because their clothing products never left the U.S. Get 20% off your first order when you use promo code STAPLE20 at american-giant.com.
This is SpaceTime, Series 28, Episode 114, for broadcast on the 22nd of September 2025. Coming up on SpaceTime, a new model to explain the cosmos. One of those ultimate questions of science and humanity, are we alone in the universe? And a partial solar eclipse darkens the skies of the South Pacific. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have developed a new mathematical model of the universe, one which attempts to explain its evolution over the past 13.8 billion years in a more simplistic manner. The new research, reported in the journal Physical Review Letters, is based on data from DESI, the Dark Energy Spectroscopic Instrument, which is measurements of the universe up to 11 billion years. The large-scale structure of the universe is sort of like a giant cosmic web, comprising strands and filaments of galaxies, galaxy clusters and superclusters, wrapped around the outskirts of vast near-empty voids. The author's work tries for the first time to explain collapsing regions of matter and expanding voids. The study's lead author, Leonardo Gianni from the University of Queensland, says it's dark energy which remains the key factor in cosmic evolution. Dark energy is a measurement showing not just that the universe is expanding, but that its rate of expansion is actually accelerating. It originally began as a sort of fudge factor called the cosmological constant, invented by Albert Einstein, whose field theories showed that the universe was in fact expanding. The problem is, Einstein lived at a time when it was generally accepted that the universe was actually in a steady state, which always remained generally the same on cosmic scales. So, to try and explain the expansion his equations were showing, Einstein invented his cosmological constant in order to artificially adjust the figures and return the universe into a steady state, as it should be. However, years later, observations by Edwin Hubble proved that the universe really was expanding. That forced Einstein to remove his cosmological constant, which he later described as his biggest mistake. Then, in the 1990s, observations of supernovae showed that the universe wasn't just expanding, but that rate of expansion was actually increasing. And so, Einstein's cosmological constant was back, but this time under the new term of dark energy. Dark because no one really knew exactly what it was. Some sort of anti-gravity or vacuum energy is the best they could come up with. Then along came David Wiltshire from the University of Canterbury, who challenged the status quo in the early 2000s. He used improved analyses of supernovae light to show that the universe is expanding in a more varied, a more lumpier way. Wiltshire's work supports a timescape model of cosmic expansion, one which doesn't have the need for dark energy because the differences in stretching light aren't the result of an accelerating universe, but instead a consequence of how science calibrates time and distance. Timescape takes into account the fact that time itself slows down around mass, and so an ideal clock in the empty space of a vast void would tick faster than what the same clock would inside a galaxy. In fact, the model suggests that a clock in the Milky Way would be about 35% slower than the same clock at an average position in a large cosmic void. And that means billions more years would have passed inside a void compared to inside a galaxy. And this would in turn allow more expansion of space, making it seem like the expansion is getting faster when such vast empty voids grow to dominate the universe. Wiltshire said his findings show that science doesn't need dark energy to explain why the universe appears to be expanding at an ever-accelerating rate. He says dark energy is simply a misidentification of variations in the kinetic energy of expansion, which is not uniform in a universe as lumpy as the one we actually live in. And that's where the new work of Gianni comes in. His research shows dark energy is real, but maybe not as strong as some have suggested. Gianni's new model can change the way physicists and cosmologists look at the universe. He points out that the standard model mapping the universe from the Big Bang right through to now has matter particles of the same size not interacting with each other. But in reality, astronomers can see there are stars and black holes, galaxy clusters and empty regions constantly interacting through forces such as gravity not accounted for by the standard model. Gianni says for the past 30 years, scientists have tried to explain what's happening as this complex universe expands, and there have been plenty of exotic attempts at solutions. You see, astronomers know that voids and collapsing regions exist, but according to Gianni, they didn't really know how to compute their impact on the measurements. And he says his model gives them a recipe to compute that figure without the need for any new physics. This new framework uses simple mathematical terms to describe how the emergence of complex structures in the universe affects cosmological measurements. Gianni and colleagues set out to identify the minimum size a void needs to be in order to impact the measurements, as well as the minimum size a galaxy cluster must have. Independent datasets, including the DESI data, were plotted against an X and Y axis chart, showing the minimum sizes of the collapsing and expanding regions of space which can impact cosmological measurements. Now, the standard model of the universe should see all of these dataset contours overlap at one end of the graph, where the sizes of the expanding and contracting regions would be too large for them to exist. But instead, they overlap in a different region, and that indicates that the large voids of space may well be responsible for the anomalous behaviour observed in the data. Gianni says the new model also helps address two of the biggest problems in modern cosmology, Hubble tension and the evidence for dynamical dark energy. Hubble tension is a discrepancy between two methods currently used to calculate the universe's rate of expansion, known as the Hubble constant. While dynamical dark energy is a theory that says energy is not constant but changing or weakening over time. The Hubble constant is an expansion rate of roughly 70 kilometres per second per megaparsec, with a level of uncertainty of around 5 kilometres per second per megaparsec, a megaparsec being 3.26 million light years. But you see, that figure depends on how you're measuring the brightness of Type 1a supernovae, stellar explosions marking the deaths of specific types of stars which are all roughly the same mass when they die, and so explode with roughly the same level of luminosity. These can therefore be used as standard candles to determine distance through the inverse square law. It's like looking at a row of streetlights down a road and being able to tell how far away each light is by how bright it appears to be. The alternative method involves observing the cosmic microwave background radiation, the leftover heat generated 380,000 years after the Big Bang when the universe's primordial quark-gluon plasma cooled enough for the first atoms to form. And you can observe this cosmic microwave background radiation today, 3.8 billion years later, as the white noise static you get between stations on old analog radio and TV sets. Of course, today that primordial super-intense heat has now cooled to just 2.7 degrees above absolute zero. And this is where Hubble tension arises, because these two different measurement methods have yielded slightly different values, creating a crisis in cosmology. Gianni says if you try to assume that dark energy is weakening, and then you try to infer how fast the universe is expanding from that data, you get even lower measurements for the rate of expansion of the universe. Solutions to one problem creating another. In his model, any weakening of energy is just a detailed accounting of what the universe looks like today. It behaves as if it were weakening, but may not be weakening at all. Gianni says essentially when asked if the complexity of the universe was showing up in the DESI data, the results shows that it was, and his study can explain those observations.
It's a new model, but what I think it's very relevant is that it doesn't really require much new physics, so it's nothing revolutionary in terms of our understanding of nature or the universe, let's say. The main point is that our previous model, our previous understanding of cosmology and evolution of the universe as a whole, was based on the fact that the universe looks the same everywhere, and it's basically describing all the matter in the universe as if they were dust particles that do not interact between each other. And this description on sufficiently, or let's say very large scale, so size of the universe wise, is working very well. However, the precision of our measurements and experiments becomes so large or became so good that we actually start to see some hint that this model could not be valid anymore. And what I did essentially is trying to give a description to take into account the fact that the universe is not made by, identical marbles everywhere, but from, structures that can vary between large filaments and clusters of galaxies and dark matter to very large voids that expand faster than the rest. So in a few words, my mathematical model is trying to quantify how many of these structures there are out there and giving to each of them some energy so that I can estimate how much their presence is altering the evolution of the universe.
Understanding the true structure of the universe and our place in it is really important for how we observe the universe and how we measure it.
Yeah, precisely. Also because, all these structures were not existing back when the universe was very young. So they actually evolved with time, just like us, and we happen to appear in one or more of these complex web of structures. When I say one or more, I mean that it's quite hard to distinguish if we live in an under-dense environment or over-dense environment, given our measurements. We, of course, have hints, but in order to understand our cosmic environment, our place in the universe, if I can be a bit dramatic, we need a lot of data and very sophisticated analysis. And this data are becoming available only now.
It's our future. Will the universe expand forever into a cosmic deep freeze? Will that expansion slow down and become a steady state? Or will gravity eventually take over from dark energy and we see the universe begin to collapse again into another big crunch, which could result in another big bang and then another big crunch? I mean, this is determining the ultimate fate of the universe.
Yeah, and all the options that you gave so far are basically all available, given our current understanding. We of course have a hint about what the nature of dark energy is, and according to this hint, what I can tell you is that it seems like the universe will expand forever. Even if dark energy is weakening, or this is at least the latest evidence from some data that are called baryonic acoustic oscillations. It seems like it's
pressure waves in the early universe.
Yes, precisely. Yeah, like if you look at the distribution of galaxies in the universe, this is not random. It's actually describing a very complex and nice pattern in which galaxies tend to or structures tend to agglomerate in certain spots and to dilute in others, reflecting somehow the initial conditions of the universe. So if to make a metaphor, imagine you are at a pond and you throw a bunch of rocks in the pond, in the water. You will see sound water waves in this metaphor. And where the crest of the waves merge together, that's where you would expect an overexcess, an overflow of water. It's the same with galaxies. We start with these initial conditions, which is like a painting or an initial setting of where the matter is distributed, more or less the same everywhere, but with small fluctuations. And then this wave propagates. And when they propagate, they tend to agglomerate galaxies in their intersection points. So again, it's not a random pattern. From the structure of the pattern, by trying to measuring it, we can understand more about what's the energy content of the universe. So how much dark energy is around, how much matter is around. It's very cool. And this probe, this cosmological probe, this baryonic acoustic oscillation, has been known for years now. But for the very first time, we have really enough observation of galaxies, I'm talking about millions of galaxies, that we can use to put on a very significant sample and statistics. So this is very exciting, and it's why it's amazing to be on the job right now for me.
Does our position within the cosmic web play an important role? In other words, if the local galactic group, that's the Milky Way, Andromeda, Triangulum, and all the satellite galaxies around us, if this local galactic group we're in is in one of these filaments, we would have a different understanding of the universe compared to what we would see or what we would experience if we were in the middle of one of these vast voids. Does that play a role in our understanding of dark matter and dark energy?
Surely does. So if I can be very simplistic, let's imagine that our environment, our cosmic neighborhood, let's say, is like a water glass. This is altering slightly our perception of what's outside the glass. Of course, light propagate within it, and so it's slightly deflected. And our cosmological inference, so what we learn about the universe, needs to keep account of this warped glass around us, which is unavoidable. Now, if you know the properties of the glass, you can kind of keep that into account and try to correct your measurements so that you are obtaining a closer description of the universe outside. However, understanding the glass itself is a very interesting field of research. So let's say that if the warped glass is very thick, like we live in an overdense region of the universe, then light will be struggling reaching us, and this will make us experience a universe that seems to expand slightly faster outside. And the opposite is true in the case of underdense glass, so if we live in a void. Now, the truth is that if we live in a void, it's quite unlikely that we are there because, by definition, voids should have less galaxies. So it would be statistical fluctuations on an unlikely scenario. And also, from what we know by reconstructing the velocity field of galaxies in the local universe, we kind of believe that we are part of a supercluster. This supercluster can be identified with an object called Laniakea, which is this massive supercluster containing hundreds of thousands of galaxies, or even a larger supercluster called Shapley, the Shapley concentration. So let's say that these hints seems to indicate that we actually belong to a overdense region of the universe, if that makes sense.
See, that's interesting because just last week we had a paper come out suggesting that the density in our region of the universe is actually lower than the average. So we're getting these conflicting figures. Depends on the observations you're making, I guess.
Exactly. That depends really on the cosmological probe you're using. And the fact that there is seemingly not a simple answer to this question kind of reflects why it's so important that we keep stress testing our models and our analysis. I should say that historically this local underdense region has been advocated and explored in the past because it was proposed early in the 2000s as an alternative to the existence of dark energy. Dark energy is a beautiful resource that we have to explain a lot of problems or a lot of seemingly inconsistent observations that become not inconsistent when you introduce dark energy.
This is Wiltshire from the University of Canterbury.
Yeah, for example, the timescape model from David Wiltshire. But I'm talking even earlier than that, like back really in the early 2000s, before the timescape model was out. People had this model called Hubble bubble, in which they were explaining or were trying to explain the apparent accelerated expansion of the universe with us living in a local void. So like a bubble in the otherwise homogeneous and isotropic universe. And of course, these type of models, including the one you mentioned from David Wiltshire, became very popular because they provide a very physical explanation to something that is a bit uncomfortable. Dark energy is a bit uncomfortable from a theoretical point of view because it challenges kind of the physics that we experience on Earth every day. So this underdense model became very popular, and in my short life as an academic, roughly 10 years, I saw them coming up over and over again several times. To my understanding, it's all about the scales you're trying to consider. If you restrict yourself only to certain scales, you might find evidence of a void. But if you shorten your window or enlarge it, you can find presence of clusters. Because it's a very complicated structure, and the name of the game is usually distances. But actually getting distances right in the universe is very hard because unfortunately we cannot build a meter as, of intergalactic size, even if we try. So we have to struggle with understanding these distances in a good way. My personal take is that I will not confidently say neither of the two, neither that we live inside a void or neither that we live inside a filament. But from a gambling perspective, it's more likely that we live in a filament if you ask me. Also, I have a work on Laniakea, this big, large supercluster of galaxies. And what I found is actually that it is compatible, like our data are compatible with a local infolding region if you interpret these velocities of galaxies as due to the fact that there is a center of gravity towards which they are falling.
So with dark energy existing but weakening, that I guess all bodes well for a big freeze ultimate fate for the universe, but not a big rip.
Yes, you are clearly talking about singularities in cosmological singularities. So big freeze will be something like the universe keeps expanding, but instead of accelerating exponentially, since dark energy is weakening, the rate of expansion is not accelerating as fast. And so everything will be put farther apart from everything else, and we end up in a cold and kind of boring universe, which at least is a perspective that is very relaxing to me compared to a big rip where everything collapses, being stretched exponentially, and even the distance between atoms is exponentially
Atoms
expanding.
get ripped apart. Yeah.
Exactly.
Very uncomfortable.
Yeah, this is a bit more uncomfortable to me, or at least
It's still a few trillion years away.
Yeah, no, I'm confident that it will be not my personal problem. Yeah, it's more of a philosophical approach, if you want. But what is really important for me to stress out is that all these data, speaking about weakening of dark energies or evidence against the standard model, are basically a strong evidence that science works very well.
That's Dr. Leonardo Gianni from the University of Queensland. And this is SpaceTime. Still to come, we ask one of those ultimate questions of science and humanity. Are we alone in the universe? And today, planet Earth experienced a partial solar eclipse, a celestial spectacle visible across New Zealand, the South Pacific, a sliver of the Australian Pacific coast, and across much of Antarctica. All that and more still to come on SpaceTime.
This is an ad by Regain Couples Therapy. Let's be honest, loving your partner doesn't mean you always like them, and guess what? That's normal. Regain, powered by BetterHelp, offers couples therapy that's flexible, affordable, and 100% online. Whether you're reconnecting or working through conflict, Regain is here to support you both. See why people wish they'd tried couples therapy sooner. Visit regain.com/couplespod to get 10% off your first month. That's regain.com/couplespod.
Bugs crashing your pack's party? Whether they've got paws or sneakers, your pack deserves a home that's protected from pests. That's where Wondercide comes in. Plant-powered protection made with steam-distilled natural essential oils that actually work. It kills and repels fleas, ticks, mosquitoes, and ants without questionable ingredients or overpowering smells. Safe to use around kids and pets when used as directed. Lab-proven to work fast. And proudly made in the USA. We offer sprays for pets, people, homes, and yards. Plus, spot-on treatments, collars, and even shampoos. Whatever your pack needs, we've got it covered. Founded by a pet parent looking for a better way to protect her dog Luna, Wondercide's now protected over 21 million lives and counting. You might have even seen us on Shark Tank. Go to Wondercide.com and use code WONDER20 for 20% off your first order. That's WONDER20 at Wondercide.com. Wondercide. Protect your pack with plant-powered Wondercide today.
Well, after that deep dive in cosmology we used to open the show, now might be a good time to ask one of those ultimate questions of science and humanity. Are we alone in the universe? And that's where a new study comes in. It reminds me a bit of that line from H.G. Wells' War of the Worlds. The chances of anything coming from Mars are 1,000,000 to 1. And the new study warns that the chances of intelligent alien civilizations existing in our galaxy aren't really much better. A report presented at the European Planetary Science Congress in Helsinki provides new speculation on the likelihood of another Earth-like society existing in our small corner of the universe. The study's authors, Manuel Scherf and Helmut Lermer, both from the Austrian Academy of Sciences, say the nearest technological civilization in the Milky Way, according to their calculations, would probably be at least 33,000 light-years away, and that such a society would need to have survived for at least 280,000 years, potentially millions of years, in order to coexist with us at the same time. They argue that just like planet Earth, their home planet would need to have an active plate tectonic system in order to regulate carbon dioxide and maintain a long-term biosphere, without which its atmosphere could become either depleted or toxic. Earth's atmosphere comprises 78% nitrogen, 21% oxygen, and trace amounts of other gases, including carbon dioxide levels, which currently sit at 0.042%, although that number is increasing every day. Sheriff and Lammer estimate that Earth will lose sufficient atmospheric carbon dioxide for photosynthesis within the next 200 million to 1 billion years, regardless of any greenhouse effect. They say their modelling suggests that planets with 10% carbon dioxide could support biospheres for approximately 4.2 billion years, while 1% atmospheric carbon dioxide would allow up to 3.1 billion years of habitability. Even so, such a world would, just like the Earth, still need at least 18% oxygen in order to support complex animal life as we know it. And that would be essential for any advanced civilization to use fire, not just for warmth and cooking, but also for metalworking and industry, a prerequisite for technology. Now, it took 4.6 billion years of planetary evolution for humans to reach that level of technological advancement. The authors say any civilization on a high carbon dioxide planet would also need to endure at least 280,000 years in order to overlap with humanity. Now, in order to live in, say, a Star Trek-style universe, a galaxy with multiple civilizations existing simultaneously, it would, according to the authors, require a societal lifespan exceeding 10 million years, compared to Homo sapiens' mere 300 to 350,000 years based on the fossil record. Sharef and Lammers say that if extraterrestrial intelligence does exist out there, it's likely to be far older than us mere humans. They also speculate that the closest advanced civilization would be on the far side of our galaxy, which I guess will be, in Star Trek terms, the Delta or Gamma quadrants. So you can forget worrying about the Klingons, Xindi or Cardassians and be far more concerned about the Borg, Kazon and Founders Dominion. This is SpaceTime. Still to come, a partial solar eclipse darkens the skies, and later in the science report, a bit of good news with the ozone hole over Antarctica being a bit smaller now than what it was in recent years. All that and more still to come on SpaceTime. Planet Earth experienced a partial solar eclipse today. The celestial spectacle was visible across New Zealand, the South Pacific, a sliver of the Australian Pacific coast, and across much of Antarctica. Partial solar eclipses happen when the new moon moves between the Sun and the Earth, obscuring a good portion of our local star. You see, usually the moon's orbit around the Earth passes a little above or a little below the apparent track of the Sun across the sky. And because the orbits of both the Moon and the Earth are elliptical rather than perfectly circular, their distance from each other and the Sun also varies. But roughly once every 18 months or so, the celestial mechanics time out just so right that everything's in alignment. The result is a solar eclipse, or in this case, a partial solar eclipse. The southernmost parts of New Zealand's South Island, including Christchurch, Dunedin and Invercargill, were the best places to see the eclipse, which took place as the sun was rising in the morning. The people there saw up to around 70% of the sun's face eclipsed by the moon in the early dawn, forming a crescent as it rose. The moon then slowly moved across the sun, blocking out more and more of its light over the next hour. As for Australia, only observers on the very tip of the east coast saw the sun be partially eclipsed as it rose above the horizon this morning. The celestial event began at 3:30 in the morning Australian Eastern Standard Time, with the partial reaching its maximum between 5:41 and 5:43 in the morning before ending at 7:54. Today's event came just 2 weeks after a total lunar eclipse, which saw parts of Australia, Europe, Africa and Asia experience Earth's shadow obscuring the full moon, turning it blood red. That entire spectacle evolved over 5 hours, starting with the first dusky bite of the moon and totality lasting a total 1 hour and 22 minutes. The sun will put on an even better display next year when its shadow crosses both polar regions of Earth. A ring of fire annular eclipse will cut across Antarctica in February. That's when the moon's just a little bit too far away from the Earth for a total solar eclipse. But then a total solar eclipse will occur over the Arctic in August, providing a spectacular show not just for anyone at the North Pole, but also for people in Greenland, Iceland and Spain. The next total solar eclipse in Australia will be on July the 22nd, 2028, with a path of totality crossing the Western Australian Kimberley coast and then passing through the Northern Territory, southwestern Queensland and New South Wales before reaching the South Pacific Ocean coast at Sydney at 2 o'clock in the afternoon. This is SpaceTime.
Finding great candidates to hire can be like, well, trying to find a needle in a haystack. Sure, you can post your job to some job board, but then all you can do is hope the right person comes along. Which is why you should try ZipRecruiter for free at ziprecruiter.com/zip. ZipRecruiter doesn't depend on candidates finding you. It finds them for you. Its powerful technology identifies people with the right experience and actively invites them to apply to your job. You get qualified candidates fast. So while other companies might deliver a lot of hay, ZipRecruiter finds you what you're looking for. The needle in the haystack.
See why 4 out of 5 employers who post a job on ZipRecruiter get a quality candidate within the first day. ZipRecruiter, the smartest way to hire. And right now, you can try ZipRecruiter for free. That's right, free at ziprecruiter.com/zip. That's ziprecruiter.com/zip. ziprecruiter.com/zip.
Bugs crashing your pack's party? Whether they've got paws or sneakers, your pack deserves a home that's protected from pests. That's where Wondercide comes in. Plant-powered protection made with steam-distilled natural essential oils that actually work. It kills and repels fleas, ticks, mosquitoes, and ants without questionable ingredients or overpowering smells. Safe to use around kids and pets when used as directed, lab-proven to work fast, and proudly made in the USA. We offer sprays for pets, people, homes, and yards. Plus, spot-on treatments, collars, and even shampoos. Whatever your pack needs, we've got it covered. Founded by a pet parent looking for a better way to protect her dog Luna, Wondercide's now protected over 21 million lives and counting. You might have even seen us on Shark Tank. Go to Wondercide.com and use code WONDER20 for 20% off your first order. That's WONDER20 at Wondercide.com. Wondercide. Protect your pack with plant-powered Wondercide today.
And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that boys who were exposed to passive smoking as a child could go on to have kids of their own with impaired lung function. The findings, reported in the journal Thorax, found that a dad's childhood passive smoking could put his kids at risk. And that risk is further heightened if those kids are childhood passive smokers themselves. The authors say the study highlights the intergenerational harms of smoking. They urge fathers to intercept this harmful legacy by avoiding lighting up anywhere near their children. Bit of good news now, Earth's protective ozone layer is healing, and the ozone hole in 2024 was smaller than it has been in recent years. The findings in a new study by the World Meteorological Organization indicate that the low level of ozone depletion last year was in part due to naturally occurring year-to-year fluctuations. However, the report also found that the long-term positive trend reflected the success of international action, with only China going against the trend, showing continued high levels of chlorofluorocarbon emissions. Compared to previous years, total stratospheric ozone cover was higher over much of the globe, and the depth of the Antarctic ozone hole in 2024, which appears over Antarctica every southern hemisphere spring, was below the 1990 to 2020 average. Chlorofluorocarbons are chemicals that destroy the Earth's protective stratospheric ozone layer. They do this by releasing chlorine atoms when exposed to ultraviolet light, creating an ozone hole and allowing harmful UVB radiation to reach the planet's surface. While once used in refrigerants and aerosol propellants, the production of most CFCs has now been phased out under the Montreal Protocols. Israel has started using the first fully operational directed energy weapon, the ion beam. The new anti-missile laser defense shield will eventually replace existing interceptor missiles like Arrow and Iron Dome, as well as the Patriot anti-missile missile. The IDF's announcement follows the deployment back in June of a scaled-down version of the ion beam platform, which has so far successfully shot down some 40 drones fired at Israel by Hezbollah terrorists financed by the Islamic Republic of Iran. The new, more powerful Ion Beam M batteries can shoot down not only drones, but also missiles, rockets and mortars, and at longer ranges, potentially even shortly after they're launched. Current IDF plans call for 3 variants of the energy weapon. The light 10-kilowatt laser beam, which is already in operation and used by ground forces for short-range targets. The new version is the Ion M variant, which fires a 250mm 50-kilowatt beam, which can be mounted on trucks and fired while mobile. And there's also a full-size directed energy weapon version, which can fire a 450mm 100-kilowatt laser beam. Well, it seems flat earthers have found a new way to try and con weak-minded people into believing their claims. Their latest spiel involves offering money to anyone who can prove the Earth is round, but they're not allowed to use science, mathematics, or even photos from space. These unfair conditions make it virtually impossible to prove the Earth is round, and so it allows the pseudoscientific community to falsely claim a victory. However, as Tim Mindham from Australian Skeptics explains, one man tried, and the matter eventually wound up in court, with contract law rather than science being the eventual winner.
This is a fellow flat earth proponent named Zen Garcia who put out a challenge for $5,000 for anyone who could provide real-world proof that the Earth is a sphere. Now, his criteria for this, you couldn't use scientific instruments, you couldn't use satellite imagery, you couldn't use math-based geodetic measurements or traditional astronomical observations. So you think, what else do we have? And he was offering this $5,000. So someone took it up. The contract said that you have to use the Ptolemaic measurement, which is of the curvature of the Earth, which is 8 inches per mile squared, which is actually not correct.
But it's not actually. Ptolemy 2,000 years ago. He proved it in Egypt.
I know he was in Egypt, but this actual figure is not exactly accurate, apparently. So what's happening is that this guy has a challenge out here for someone to prove this measurement system, which is not exactly accurate, without using any other sort of scientific equipment. Now, someone did it. They claimed they did it. The guy didn't pay up. So the person who supposedly sort of proved the Earth was round took the flat earther to court, and the court knocked it out. Said, no, you can't get your $5,000. And a lot of people saying, who are science-based, saying, hang on a second, this guy is saying the Earth is flat, and in a court of law you're saying it is. No, the thing is that the judge wasn't saying the Earth is flat. He also wasn't saying it's round. What he was saying is that it's a legal contract, and you didn't comply with the ridiculous elements of this legal contract. So
does that have any implications for you guys at Skeptics? Because you have a very substantial reward for anyone who can prove pseudoscience.
Yeah, we get $100,000 under scientific conditions. Now, they're agreed conditions. The skeptics don't set the rules. It's that the conditions are agreed by both sides, right? It's not like I'm going to set up this thing and you have to do it, right? This is to say, let's find out a way to test this particular claim. Flat Earth is a bit different because it's not their specific claim of something skill that they have.
Well, you just got to watch a boat sailing over the horizon.
You've got to have both sides have to agree it's a fair test beforehand, otherwise the test doesn't go ahead for our $100,000 challenge. And we've had people apply for it, and we've tested people, and they, so far no one's been able to prove that they can do the things they say they can do. But this particular thing I'm proving the flat Earth is a very similar thing to what happened in the 1800s with a fellow named Alfred Russel Wallace, who was one of the developers of the theory of evolution. He was also a scientist in many different areas, and someone else put up this thing, proved the Earth is a sphere, and he went and did an experiment on a canal, did posts and all sorts of things, and proved quite definitively that the Earth was curved. And then the guy said, no, we're not going to pay you. So he took him to court, and it went on and on and on. Wallace ended up paying more money for the court than he would ever have got for the challenge amount. So this is very similar.
But it's the principle of the thing that counts.
It is the principle, but in this particular case, there was a money principle, not the scientific principle. So people are disappointed that in a court of law, the flat Earth theory was not thrown out as ridiculous. And the story goes is that the law was not looking at the science. It also wasn't necessarily looking at how reasonable the conditions were. It's just that the challenger did not comply with the unreasonable conditions. So that would then be used to say, see, the court of law, they didn't knock back flat Earth. They clearly said this is a contract issue, not a scientific issue, unfortunately.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.